Okay, we're back. We're gonna talk about a couple of slides. Work in thermodynamic processes. Bring the PowerPoint up. And here we are. Okay. You remember the expression shown for the internal energy of an ideal gas. This expression is valid only for a monatomic ideal gas, which means the particles of the gas consist of single atoms. Uh, the change in the internal energy, delta U, for such a gas is given by this equation. Um, that's the change in the energy. The molar specific heat at constant volume of a monatomic ideal gas, CV, is defined as shown here. Um, the change in internal energy of an ideal gas can then be written as delta U equals N, the number of moles, CV delta T. The change in internal energy of an ideal gas can then be written, I think I already said that. For ideal gases, this expression is always valid even when the volume isn't constant. The value of the molar specific heat depends on the gas and can vary under different conditions of temperature and pressure. A gas with a larger molar specific heat requires more energy to realize a given temperature change. The size of the molar specific heat depends on the structure of the gas molecule and how many different ways it can store energy. That's the degrees of freedom. Sometimes you can vibrate this way, sometimes it vibrates up and down, sometimes it vibrates like this. So it's the different vibration modes that store energy. A monatomic gas such as helium can store energy as motion in three different directions. A gas such as hydrogen, on the other hand, is diatomic in normal temperature ranges, and aside from moving in three directions, it can also tumble, rotating in two different directions. So hydrogen molecules can store energy in the form of translational motion, and in addition can store energy through tumbling. Also, molecules can store energy in the vibrations of their constituent atoms. A gas composed of molecules with more ways to store energy will have a larger molar specific heat. Each different way a gas molecule can store energy is called a degree of freedom. Each degree of freedom contributes 1/2 R to the molar specific heat. Because an atomic ideal gas can move in three directions, it has a molar specific heat capacity, CV, equals 3 times 1/2 R equals 3/2 R, where R is 8.31 joules per mole Kelvin. A diatomic gas like molecular oxygen, O2, can also tumble in two different directions. This adds 2 times 1/2 R equal R to the molar specific heat. So CV equals 5/2 R for diatomic gases. The spinning about the long axis connecting the two atoms is generally negligible. Vibration of the atoms in a molecule can also contribute to the heat capacity. Generally, molar specific heats must be determined by experiment. Okay, and now we've got a little table. This table is a representative values of CV are shown in the table. If we take R to be 8.31 joules per mole Kelvin, then generally the monatomic gases are 3/2 R, the diatomic gases are 5/2 R, and the polyatomic gases are 6 to 7/2. So you can take this table and do some calculations yourself and prove that that's true for you. You should be able to check it out. I thought I did a spreadsheet, but I couldn't find it. I did, let's see. Well, I won't bother doing that. I did do it on Mathematica. I use Mathematica for a lot of my calculations. Okay. And next, we're going to talk about thermal processes in gases. But for right now, we're gonna stop here. Stop share. Stop